Good evening, guys. My name is Ganesh Shankar Bhandari, and I have I am the TA of NPTEL course Principle of Casting Technology, taught by Professor PK Jha, and I am here to uh, record the video for live session week 3, which was not recorded previously due to some technical glitch in the last session on Sunday. Um so I will quickly go through with te- what we have discussed in the live session on Sunday. So I will go through quickly with my slides or presentation, whatever questions we have discussed in the live session. So first we have discussed the about the casting terminologies. So we have discussed about the casting terminologies. We have discussed the pouring cup, riser system, core, and down sprue or drag systems in the sand casting. And we have discussed about pouring basin, how this pouring basin and runner screw works, and what is the aspiration effect. To avoid the aspiration effect, generally the sprues are made some in a tapered direction with some angle. Maybe it can be downwards or it can be upwards angle. Then we have discussed the purpose of gating system. A gating system should be able to do the following: permit complete filling of the mold cavity, requires minimum time to fill the mold cavity, then minimum turbulence so as to minimize gas pickup, and regulate the rate at which molten metal enters the mold cavity, because this is a very uh, important thing during a casting process, because you have to decide the time of solidification uh, of the material, because whatever the material you are taking, it will solidify maybe very quickly, or it can solidify very late. So you have to decide the rate of molten metal pouring in your mold cavity. So you have to design your gating system according to that. Prevent unwanted material from entering mold cavity. We generally use a filter material for that purpose. Establish suitable temperature gradient, no mold erosion, simple and economical design, easy to implement and remove after solidification, and maximum casting yield. Now we will discuss some MCQ questions. So coming to first MCQ question, it is a common practice to enhance the desk of core sand by adding wood floor. So we have discussed the right answer was collapsibility, because when we are going to make a core, it will be like this is a casting, and this is a cavity. So to create this cavity, we use core material to create this cavity inside the casting. Okay, so making this core, we use some core sand, and providing collapsibility to this core sand, we use wood floor, because after casting we have to remove this core. So it has to be easier to collapse. Then in method of ramming, a stream of sand is thrown at high velocity onto the pattern. The answer was slinging, because we are talking about high velocity. So when we throw the uh, sand in a high velocity, it is known as slinging. Then which of the statement is not correct for evaporative pattern casting? The answer was it uses plaster of Paris for pattern making, uh, because when we are talking about evaporative pattern casting, so we talk about generally investment casting or full mold casting type of material, and we generally want a material which can be easily evaporated when we are going to pour the molten metal into our casting pattern. So the molten metal will take the cavity of that pattern, and the pattern material will get evaporated from that casting. So we cannot use plaster of Paris for making pattern, because it will not get evaporate during the molten metal pouring, because plaster of Paris has a evaporation temperature of around 1900 or 2000 degrees Celsius. So it will not get evaporate, and it will ruin your casting. Then coming to next question, is an dash is an open space in the mold for positioning, locating, and supporting the core. So we generally make core prints for supporting the core material when we are talking about casting. If this is a core, okay, so this is a core pattern. So for hanging this core pattern, we generally make some core prints inside the molds so that we can easily hang this core inside our casting material wherever we want. Which type of casting is also known as cavity-less casting. So when we talk about cavity-less casting, we talk about full mold casting, which is known as cavity-less casting. Then coming to next question, we have discussed which of the following is our advantage of top gating system. So when we are talking about top gating system, we talk about this is our casting pattern and this is the sprue. So in top gating system, the material will be poured from the top side of the melt, and in that case the sprue material itself can be used as a riser also. So the proper temperature gradients are formed and directional solidification towards the riser located at the top of the casting can be achieved. Yes, that can be achieved, and the gate themselves may be made to serve as riser. As we can see, this is sprue material. So the material, if we are going to fill the material in this sprue until the top of the sprue, and if we can cover it with some material which can help to reduce the heat losses from this surface. So this sprue can also act as the riser system. So both answers are correct. So both first and second will be are the correct option. Then which of the following statement is correct? The sprues are generally tapered upward to avoid aspiration of air. If sprue of uniform cross section is used, severe aspiration may occur because the metal velocity increases downward the vertical sprue. Deeper and enlarged sprue base cavity serves as a cushion to the falling weight of the metal and absorbs its kinetic energy. So when we talk about first point, the sprues are generally tapered upward to avoid aspiration of air. So this point is not correct because we can make the sprues can be upward or downward tapered in both way. Just we have to avoid the aspiration of air. So this is incorrect statement. Then sprue of uniform cross section is used. If we are going to use a uniform cross section sprue like this, then it will create during the molten metal pouring. So molten metal flow will be like this. So due to this molten metal flow, this area will not going to be have any molten metal. So due to this air entrapment here, the aspiration effect will come into existence. So avoid this to avoid this aspiration effect, we have to make the sprue with some taper angles. So this statement is correct. Then deeper and enlarged sprue base cavity serves as a cushion to the falling weight of the metal and absorbs its kinetic energy. When we talk about sprue base, it is like this. So when molten metal is pouring with a high velocity speed, so what it will do if we are not going with the sprue base, so it will erode the sand from here and it will create the sand will come into your casting, and it will uh, it will add up the impurities in your final casting. So the what the sprue base is going to do, it is going to absorb all the kinetic energy of this molten metal uh, falling with high speed, and the it will regulate the flow inside your cavity. So the second and third will be the are the correct one. Then coming to next question, gating ratio is defined as. So when we talk about gating ratio, we the easiest route to remember the gating ratio is to remember the molten metal direction, the flow of molten metal direction. So molten metal direction will flow from the sprue from your sprue. Then after sprue, it will go into the runner system, and after runner system, it will go inside your cavity from the gate. So the gating ratio will be defined as area of cross sectional area of sprue ratio cross sectional area of runner, then cross sectional area of gate. So gating ratio is defined as sprue area, total runner area, and total in-gate area. So when we talking about the word total runner area and total in-gate area, because runner we can use now max different number of runners into your system. Generally it should be in the even number, 2, 4, 8, or we can use 1 also. Then total in-gate area, we can use many number of gates into your casting system. So gating ratio will be defined as sprue area to total runner area to total in-gate area. And coming to next question, which of the following statement is are correct for pressurized gating system? So when we talk about pressurized gating system, we talk about the as it keeps itself full of metal, the danger of metal pulling away from the walls with consequent air aspiration is thus minimized. Yes, high metal velocities in a pressurized system may tend to cause severe turbulence at the junctions and corners and in the mold cavity. Yes, this is also right, because when we talk about pressurized gating system, so the area of runner will be greater than the area of the gate. So according to the velocity momentum or speed momentum law, a1 v1 equal to a2 v2, when the area of the when if runner area is a1 and velocity of the molten metal is v1 inside this area, so when we are going to minimize the area of gate, so obviously the velocity of the molten metal from gate area will get increased, so it will create high metal velocity. And in a pressurized system, it will create severe turbulence, and it can erode the corner parts of your metal casting, and due to that sand may come into your metal casting and act as a impurity material. Then coming to next question, which of the following statement is are correct for unpressurized gating system? So when we talk about unpressurized gating system, in this type of gating system, the area of runner will be lower than the than your area of gate. So according to velocity momentum law, uh, the velocity on the gate will get decreased due to because runner has a lower cross sectional area as compared to gate. So the answer will be second only, because it will not produce high metal velocity and permit lower flow rates compared to pressurized gating system. That this statement is incorrect. It reduces turbulence in the gating system because there will be no pressure on the uh, mold wall, so it will reduce the turbulence in the gating system. So answer will be second only. And then coming to next question, in a gating system the ratio 1 raised to 2 raised to 4 represents. So as we talked about, the gating ratio is defined as the defined according to the molten metal flow direction. So molten metal flow direction will be sprue base area to total runner area to total ingot area. So the gating system ratio will is representing sprue base area to total runner area to total ingot area. Coming to next question, gate is provided in molds to feed the casting at a constant rate. Yes, this is true. Give passage to gases. No. For passing of gases, we generally make some holes in our casting so that gases can be easily passed from those holes. Compensate for shrinkage? No. For compensation of shrinkage, we generally use riser, or we can use the sprue material, or if we are going with the top gating system only, then we can use those gates. Then we don't need to provide any gating system. The sprue can act as a riser system, so it can compensate shrinkage also. Avoid cavities? No, gate cannot be used for avoid cavity. So gate is provided in the molds too only. The answer is feed the casting at a constant rate. Then coming to next question, we have discussed numerical. A mold has a down screw whose length is 20 centimeter and the cross sectional area at the base of screw is 0.5 centimeter square. The down screw feeds a horizontal runner leading into the mold cavity of volume 1000 centimeter cube. Gating ratio is given. The time required to fill the mold cavity will be. So for the flow rate, we know Q equal to volume of casting, whatever we are going to fill, upon that upon the velocity of the molten metal. So according to the top gating system, in the top gating system, when we are talking about a top gating system, so the velocity of the molten metal into that casting will be root of 2gh. So we can easily calculate the velocity of the molten metal into the system, because we have G as 981 centimeter and H is given as 20 centimeter, sprue whose length is 20 centimeter, so H is given. So we can easily calculate the V, and after calculating the V, we can just put it into Q equal to V upon V2. So we will get the answer. Okay, coming to next question. The down screw leading into the runner of a certain mold has a length 175 mm. The length is given. The cross-sectional area at the base of the sprue is 400 mm square, that A2 is given. Then the casting volume is given. The mold cavity has a volume equal to 0.001 meter cube. Determine the velocity of the molten metal flowing through the base of the down screw. So we can easily calculate the velocity here with the formula V equal to root 2gh. And then coming to the volume rate of flow. So volume rate of flow can be calculated with Q equal to V volume of casting upon the cross-sectional area. Then the time required to fill the mold cavity, we can easily calculate the time required also according to our flow rate. So the V can be calculated with the help of formulation root 2gh, then Q equal to V into area, and T equal to V upon Q. So we can easily calculate the three things according to these formulations. Then coming to next question, the flow rate of liquid metal into the down sprue of a mold equal to 1 liter per second. The cross sectional area at the top of the sprue equal to 800 mm square. The cross sectional area of the top of the sprue is given and its length is given 175 mm. What area should be used at the base of the sprue to avoid aspiration of the metal? So when we are talking about the aspiration of metal, we generally talk about the tapered type of sprue. So here we can just calculate the area of the sprue with the help of velocity momentum law V1 A1 equal to V2 A2. So we have A1, we have uh, the velocity here 1 liter per second, and we have the height. So we can easily calculate the flow rate here with the help of V equal to root 2gh. Then get after getting the V2, we can easily calculate the area of the sprue at the down direction. So as we can see, we have to calculate A2, then V2 equal to, we can easily calculate with the root 2gh. We can calculate the V2, and we have Q equal to V1 into A1 equal to V2 into A2. So A2 will be 539.67 mm square. Coming to the next question. Uh, a molten metal can be poured into the pouring cup of a sand mold at a steady rate of 1000 centimeter cube per second. So Q is given. The molten metal overflows the pouring cup and flows into the down sprue. So it is going into the down sprue. The cross section of the sprue is round, okay, with a diameter at the top 3.4 centimeter. If the sprue is 25 centimeter long, determine the proper diameter at its base so as to maintain the same volume flow rate. So we can easily go with the we can calculate the V2 here, and with the help of A1 V1 equal to A2 V2, we can calculate the diameter of this area. First we will calculate the area here, and from area we can calculate the diameter. So we have given Q, D1, H, and D2 we have to calculate. So we can first we will calculate the V2 here with the help of root 2gh. Then we have Q equal to V into A. So we can calculate the D2. It will come 2.39 centimeter. Then coming to next question. In a gating system design, a down sprue of 180 mm length has a diameter of 20 mm at its top end. The liquid metal in the pouring cup is maintained up to 60 mm height. The diameter in mm of the down sprue at its lower end to avoid aspiration will be. So we have make a we will first make the diagram according to the description given in the question. So we it is showing that we have a pouring cup which is filled up to 60 mm height, and after pouring cup we have a sprue with a cross sectional area diameter of 20 mm. Then the height of the sprue is 180 mm. So we have to calculate this D2. So for calculating D2, first we have to calculate the area of sprue here. So with the it is showing that its lower end to avoid aspiration will be. So we can go with this formula R equal to root SC upon H equal to AG upon AS. So we have the area, we have to calculate this area of gate, we have the area of sprue here, so we can easily calculate the diameter here. Then coming to next question, dimension of the cavity is given and the sprue height is 5 inches and its area is 1 inch square. Find the pouring time in the top and bottom gating system. So with the help of these two, there are different formulas for pouring time in top gating system and bottom gating system. For formulation in top gating system, the time will be volume upon area of gate into that velocity 2GHS. And for bottom gating system, the formula we will use TB equal to AC upon AG into 1 upon root 2G into 2 root H minus SC. But here we have given only sprue height. We have not given any pouring cup height. So that SC will become your sprue height only. So H minus SC will become 0. So the formulation remain will be TB equal to AC upon AG into 1 upon root 2G into root 2H. So we have H 5 inches, G is given in inches per centimeter square, and we have the area of casting, cross sectional area of casting, and we also have the area of gate. So we can calculate the time required for filling for bottom gating system. Coming to next question. A mold cavity of 1200 centimeter cube volume has to be filled through a sprue of 10 centimeter length feeding a horizontal runner. The cross sectional area at the base of the sprue is 2 centimeter square. Take G equal to 9.81 meter per second square, neglecting frictional losses due to molten metal flow. The time to fill the mold cavity is in seconds. So here we have given that it is a top gating system, so we can easily go with the formulation T time of filling equal to Q upon AG into V we can calculate with the help V equal to root 2GH. So we can easily calculate the time of filling for this mold cavity. So this is the end of session.